I explained what exactly static VI characteristics of a diode. Then with respect to power diode, the another concept is concentrate on the switching characteristics of a diode. That I told already. The switching characteristics are very important characteristics of a power diode. To select a diode for particular frequency of application, then mainly concentrate on switching characteristics. The switching characteristics are mainly, we can discuss in two conditions. One is turn on condition and turn off condition. That's why I want to explain these characteristics. What exactly turn on characteristics? These are the characteristics of diode during turn on. Then I want to discuss what is the turn off characteristics. That is, these are the characteristics of diode during turn off condition. Concentrate first what exactly turn on characteristics of a diode. This concept is switching characteristics. This is switching characteristics of a diode. Yes, this is switching characteristics of diode. Switching characteristics of diode. This is concept is switching characteristics. Okay. In this switching characteristics, again turn on characteristics, and other one is turn off characteristics of a diode. Turn off characteristics. Okay. Now we'll see what exactly a turn on characteristics of a diode. The first one is turn on characteristics. Turn on characteristics. Concentrate on turn on characteristics. Okay. The turn on characteristics is, once you draw the what is the turn on characteristics of a diode during turn on. These are the characteristics of a diode. We know that during turn on of SCR, the current is rising to rated current. Like this is the forward current characteristics of diode. Forward current characteristics of diode. Okay. Now, how the voltage across the diode is changing during turn on. This is time axis. This is time. How the voltage across the diode is changing during turn on. That you concentrate. This is a forward voltage across the diode. Now the forward voltage across the diode is changing like this. This is forward voltage drop, on state voltage drop. Okay. Okay. This time is called, whatever the time we can define here, this time is called forward recovery time. This is TFR. This is forward recovery time. Okay, forward recovery time. Then this current is forward recovery current. Forward recovery current. That means initially diode is under reverse bias condition. This is negative voltage. If the forward voltage is applied to the diode, the forward current is rising. One observation here, during turn on of SCR, the voltage across the diode reaches to maximum value. The voltage across the diode appears a large value. That means a large voltage is appear across the diode during the turn on. Sorry, this is forward recovery voltage. This is forward recovery voltage. VFR, forward recovery voltage. Understood? That is, during turn on, a large voltage will appear across the diode. Once it is completely turned on, the voltage across the diode is equal to on state voltage drop. Understood? That means observation is here, where TFR is forward recovery time, forward recovery time, forward recovery time, forward recovery time. Let this time is taken as T1 and this time is taken as T2. Yes. Then forward recovery time equal to T1 plus T2. In power diode, this time is in the order of 10 microseconds. This time is nearly equal to in the order of 10 microseconds. That means turn on is nothing but the current through the diode is rising to rated current. Okay. This is IFR. IFR, forward recovery current. This current is nothing but a forward recovery current. Understood? Now, this is forward recovery. This is forward recovery voltage. This is forward recovery voltage. That means during turn on transition, during turn on transition, a large voltage appear across the diode, a large forward recovery voltage appear across the diode, as compared to on state voltage drop. That means because of rate of change of current, a large recovery voltage will appear across the diode as compared to on state voltage drop. On state voltage drop means when the diode is completely turned on, the voltage across the diode is this one. This is in the range of 0.5 volts to it may be is equal to 1.5 volts. That depends on the rating of the diode, that will be changes. Then this forward recovery voltage is in the range of 10 volts to 30 volts. See the difference. If the suddenly a forward voltage is applied to the diode starts the conduction. But suddenly it is not reaches to the rated current now. There is slowly current is changing to rated current. Slowly current is rising. During this process, a large forward recovery voltage will appear across the diode. It is in the range of volts, that is 10 volts to 30 volts. Okay. But what is the on-state voltage drop? It's very small, that depends on the rating of the diode. Generally, this is the forward recovery voltage. Understood or not? That means the forward recovery voltage depends on rate of change of forward current. Understood? The point to remember, mainly VFR depends on forward recovery voltage. VFR depends on DIF by dt. That is rate of change of forward current. If the rate of change of forward current through the diode is high, then the forward recovery voltage is also high. Understood or not? This about what exactly switching characteristics. In this switching characteristics, this is the turn-on characteristics of a diode. Once the diode completely starts the conduction, the voltage across the diode is very small voltage drop, that is equal to forward voltage drop. This small value indicates that forward voltage drop or on-state voltage drop. Clear? Okay. This is turn-on characteristics. The turn-on character, the time taken to turn on the diode is nothing but a forward recovery time. This much of time is taken for turn on of the diode. That is a forward recovery time. This much of time is taken for turn on of the diode. Understood? Now we concentrate on what is the turn off characteristics of a diode. This is very important. Turn on is nothing but a change of device conduction from reverse bias to forward bias, or reverse bias to forward bias, that is forward conduction up to conduction, that is nothing but a turn on. Initially, let us assume that diode is under reverse bias condition. If the forward voltage is applied, changing from reverse to forward, this time is nothing but a forward recovery time. Clear? Now we concentrate on what is the turn off characteristics of a diode. Understood? Concentrate on turn off characteristics. Here I want to draw the what is the turn off characteristics. Yes, this is a turn off characteristics. A turn off characteristics or reverse recovery characteristics of a diode. A reverse recovery characteristics of a diode. A recovery characteristics of diode. Reverse recovery characteristics of diode. Turn off characteristics or reverse recovery characteristics of diode. So, okay, this is a reverse recovery characteristics of diode. First, I want to draw what is the total turn off characteristics of a diode. Later on I will explain what the significance of these characteristics. First you draw these characteristics, parallelly you draw this. What I am drawing the characteristics, parallelly you draw these characteristics. Yes. This is time axis and this is the forward current. Yes. This is the forward voltage across the diode. This time. Yes. This is 1 by 4 IR, maximum value of 25% of maximum value of reverse recovery current. Yes. Let this time is I am considering as a TA and this time is TB. Yes. This time is taken as TB. Significance of T and TB that I will give. Okay. Then this is forward voltage drop across the diode. This is the forward voltage drop across the diode during the conduction. Yes. Then go through with how to draw the power loss. This is power loss in a diode. This is power loss. Yes. This is power loss is like this. Yes. This is forward current, forward voltage across the diode, and this is the power loss in a diode during turn off. That means even though forward current is 0, here the diode is conducting. At this point forward current is 0. Let a reverse voltage is applied across the diode, then the forward current is 0. But even though forward current is 0, the diode is not stops the conduction. The diode is continuously conducting because of stored charges in junction and layers. Because of minority charge carriers or because of stored charges in junction and layers, the diode is continuously conducting. That means even though reverse voltage is applied at this instant, the diode is not stops the conduction. But the diode is continuously conduct in reverse direction because of stored charges. Then diode is continuously conduct because of stored charges means the turn off time will be increased. Understood? When the diode is perfectly turned off, then the total current through the diode is 0. Then only we can say that the diode is perfectly turned off. Actually, this time is taken as a reverse recovery time. This time is called reverse recovery time. For example, let assume that initially diode is forward bias and it is conducting. This is P layer and this is N layer. We know that in P layer means majority carriers are holes. Holes are the majority carriers. That is positive charge. In N layer, which are the majority carriers? electrons are the majority carriers. Electrons are the majority carriers. This concept you know that I am giving just for fundamental. Electrons are the majority carriers. In which layer? N layer. N layer. Okay. Here which is the minority carrier? Electrons are minority carriers. Which is the minority carriers here? Holes are positive charges, minority carriers. Now for this, let us assume that initially diode is under forward bias condition. If the diode is under forward bias condition means anode is connected to positive plate, then cathode is connected to negative plate. Then we can say that anode to cathode voltage is positive. Then the diode is forward bias. Understood or not? Now, because of this positive plate, these holes are having the positive charge. Then all these positive charge are repelled from the positive plate. Then holes are moving like this. This is the direction of the hole. Then because of this negative plate, electrons are having the negative charge. All the electrons are repelled from this negative plate. Electron is moving like this. That means always the direction of current is opposite to electron direction or in the direction of hole direction. This is the direction of forward. That is the forward current is exists from positive to negative. Understood? That means if the diode is under forward bias condition, which carriers are crossing the junction? You tell me. This positive charge is crossing the junction. This negative charge is crossing the junction. That means which carriers are crossing the junction? Majority carriers are crossing the junction. Because of majority carriers are crossing the junction, we are getting a high anode to cathode current that is treated as a forward current. The direction of that forward current is externally from anode to cathode, that is positive to negative. Understood? Now, this is under diode is under on condition. Now, this much of current is conducting. This is the current through the diode. Let us assume that. Now, in order to turn off the diode, here I am explaining the turn off characteristics now. In order to turn off the diode, now what we are doing means we are applying the reverse voltage. Now what happened? Now for this diode, now we are applying a reverse voltage. Now we are applying a reverse voltage. To turn off the diode, a reverse voltage is applied. Then which is the majority carriers here? Holes is the majority carriers. Positive charge is majority carriers. Positive charges. Which are the minority carriers? Electrons are minority carriers. Then which is the majority carriers here? Electrons are majority carriers. Electrons are majority carriers. Which are minority carriers? Positive charges, minority carriers. Now this is anode and this is cathode. To make the diode is under reverse bias condition. This is under forward bias condition. It is under reverse bias condition. To make the diode is under reverse bias condition, anode to cathode voltage must be negative. If you want to make anode to cathode voltage is negative means anode is connected to negative plate, cathode is connected to positive plate. Now because of this polarity, all the positive charge is attracted by negative plate. Then holes are moving this direction. All negative charge attracted by this plate, then electrons are moving this direction. That means, is there any crossing of majority carriers? No. When the majority carriers are not crossing the junction, then slowly the forward current is zero. When we are getting forward current? Because of crossing of majority carriers. But is there any crossing of majority carriers? No. That's why slowly the forward current falls to 0. But even though forward current is 0, but still there exists a current due to minority charge carriers. Which carriers are crossing the junction, you tell me? Yes, sir. Because of this negative plate, whatever the minority carriers in the P layer repelled from the negative plate crossing the junction. Again, these minority carriers are crossing the junction. Okay, this negative is crossing the junction, this positive is crossing the junction. That means, that's the reason why, even though forward current is 0, diode is continuously conducting because of stored charges in junction and layers. Then it continuously conducts, reaches to peak value, then slowly all those charge carriers are recombined, then slowly that current is falls to 0. Then we can say that diode is perfectly turned off. Understood or not? When the diode is perfectly turned off, then the total current to the diode is 0. Then we can say that diode is perfectly turned off. This is the reason why diode is conducting some extra time even though forward current is 0, means because of stored charges in junction and layers. Understood or not? Now that means that statement I am right. You write, note down this one. That is, even though forward current is 0. That is, even though forward current is 0. Even though forward current is 0. Even though forward current is 0. Forward current is 0. Current is 0. The diode is continuously conducting. Diode is continuously conducting because of stored charges because of stored charges in junction and layer. In junction and layers. In junction and layers. Yes, because of stored charges in junction and layers. Due to this extra reverse recovery current, actually this current is taken as a reverse recovery current. Okay. Due to this extra reverse recovery current, the turn off time of the diode is increases. Then when the turn off time of the diode is increases, the switching rate, that is the frequency of operation, increases or reduces? Think, it is reduces. Why? Turn off time is increases na. The total time of operation is nothing but on time plus off time. Once the total time of operation, turn off time is increases, means the total the time of operation is nothing but on time plus off time. Off time. If the off time is increases, then what the total time of operation increases. If the total time of operation is increases, then what the frequency of operation reduces. That is, due to this process, what happening? What the drawback? Due to this, the turn off time of the diode is increases. The turn off time of the diode is increases. And the frequency of operation is reduced. The switching frequency is reduced. The frequency of operation is reduced. Understood? That is, when the diode is perfectly turned off, whenever the total minority charge carriers whenever this total stored charge is recombined, then only we can say that the diode is perfectly turned off. Whenever this total minority charge carriers are stored charges is recombined, then only we can say that the diode is perfectly turned off. Then during reverse recovery process, this process is nothing but a reverse recovery process. During TA time, whatever the stored charges in layers are removed, the stored charges in the layers is removed during TA time. Okay. During TB time, the stored charges in the junction is removed. Whatever the stored charges at the junction is removed. Then this total time is nothing but a reverse recovery time. Here we are giving what is TRR. The TRR is nothing but a reverse recovery time. Where TRR equal to reverse recovery time. TRR equal to TA plus TB. This is called reverse recovery time. Reverse recovery time. This is a reverse recovery time. During this time, stored charges in layers is removed. Layers is removed. Understood? During TB time, stored charges in junction is removed. Stored charges in junction is removed. Stored charges in junction is removed. During which time? TB time. Then that is nothing but a reverse recovery time. Okay. Then where IRM equal to maximum value of reverse recovery current. Maximum value of reverse recovery current. Reverse recovery current. Maximum value of reverse recovery current. IRM equal to maximum. This maximum value. This current is nothing but a IR. This is maximum value of reverse recovery current. This is the rate of change of current. Let this current is di by dt. Rate of change of current. Then can you define what is the slope of this curve? Slope of this curve. Shall we write like this? The slope of this curve is defined as. Rate of change of current. Then from this one, how to write rate of change? di by dt equal to IRM by TA. Di current, dt time. Then from this, what is IRM? IRM equal to TA into di by dt. You write one expression here. What is this IRM equal to TA into di by dt? This is IRM. This is the maximum value of reverse recovery current. Here I want to define what is reverse recovery time. For reverse recovery time, you can give the two definitions. One definition is it is time taken for the reverse recovery current. That is simple definition. The another definition is the time between at the instant of forward current 0 to 25% of the fall of reverse current is 25% of IRM. That time is taken as a reverse recovery time. Okay. Here we are defining the reverse recovery time. Okay. This over. Okay. We can define what is the reverse recovery time. Reverse recovery time is defined as. One definition is it is time taken. For reverse recovery current. Reverse recovery current that is denoted by IRR. Reverse recovery current IRR. Okay. Or we also define like it is time between it is time between at the instant of forward current 0 to forward current 0 to 25%, 1 by 4 na 25% of IR. Very important definition. Based on this statement, already question is framed in compute. The reverse recovery time of the diode is defined as it is time between at the instant of forward current 0 to 1 by 4 IRM. 1 by 4 IRM means 25% of IRM. This time is taken as a reverse recovery time. With this knowledge, now I want to do some analysis based on these characteristics. Point to remember, these are the this is for the current characteristics. This is for voltage character. This is the power loss across the diode during the turn-off process. Power loss is defined as voltage into current. This is negative current, then this is positive voltage. Power loss is negative. Negative into positive, negative. Negative current, negative voltage. Negative current and negative voltage. Then power loss is positive. That means during reverse recovery process, there exists some power loss. During turn-on process also there exists a power loss because both voltage and current is exist. During turn-off process also there exists some power loss. Understood or not? Okay. Then this is about what exactly? Turn-off characteristics or reverse recovery characteristics of a diode. But here I want to do some analysis here. Okay. What is the analysis means? Let's assume reverse recovery characteristics are a triangle. Let's assume that the reverse recovery characteristics of a diode is a triangular characteristics. If you assume that it is a triangular characteristics, then what the area under the curve indicates? The area under the curve indicates what parameter? Let's assume that for approximate analysis, this I am doing some analysis here. This is approximate analysis. Okay. For approximate analysis, let's assume that the reverse recovery characteristics of diode is a triangular characteristic. Let these characteristics are triangular. Okay. For approximate analysis, let's assume reverse recovery characteristics are triangle. Reverse recovery characteristics are triangular or triangle. Then what is the area under the curve? Then this area under the triangle, what it indicates? Then area under triangle equal to what indicates, you tell me? What is this curve? Current curve, no? This is the current. It may be it reverse recovery current, no doubt at all, but it is a current. What the area under the current curve indicates? Which parameter? Area under current curve indicates which parameter? We know that Q equal to di by dt. Q equal to, how to define? I equal to current equal to dq by dt. dq by dt. Then what Q equal to? Integral I dt. Integral I dt means this is the area under current curve. Area under current. Then area under the current curve indicates charge. That's why area under triangle indicates this is reverse recovery charge, QRR. This indicates the reverse recovery charge. Reverse recovery charge. It indicates the reverse recovery charge. Then what is the reverse recovery charge QRR equal to? Tell me. What is the reverse recovery charge QRR equal to? Okay. Then reverse recovery charge QRR equal to. Here there existed two right angle triangles. Now this is one triangle and this is another triangle. Area under this triangle plus area under this triangle. Then what is the area under this triangle? Half into TA into IRM plus this area under this triangle also calculate half into TB into IRM. Then what is QRR? Reverse recovery charge equal to half into IRM into TA plus TB. Then what you get? Reverse recovery charge equal to half into IRM into TRR. This is one equation. Very important that you concentrate. QRR equal to 1 by 2 IRM into TRR. Understood or not? Okay. This is reverse recovery charge. That is the stored charges. Reverse recovery charge are stored charges in junction and layer. That means how much charge is stored. This is reverse recovery charge. Reverse recovery charge or stored charge. Stored charge in junction and layers. That is 1 by 2 IRM into TRR. We know that. What is IRM equal to? We know this. IRM equal to what is IRM equal to? TA into di by dt. This you know. This is equation 1 and this is equation 2. For approximate, this is not exact analysis. Assume that approximate. Let TA is nearly equal to TRR, then IRM is nearly equal to IRR. Then you also write then QRR equal to 1 by 2 IRR into 1 by 2 IRR into TRR. Then what is IRR equal to? TRR into di by dt. This is also we can apply based on the analysis. If data regarding to TB is not given, you take TA equal to TRR. Then during that time the current is taken as a IRR, where IRR is nothing but a reverse recovery current. Understood? Okay. Actually, this is exact formulas. Then you also simplify the formulas like this. Let TA is nearly equal to TRR. That is, we are neglecting TB. But if TB is given, then you go for this is exact formulas. Understood? Okay. But you also write like this. QRR equal to 1 by 2 IRR into TRR. IRR equal to TRR into di by dt. There is no data regarding to T and TB separately. Then you go for directly IRR equal to TRR into di by dt. Clear? Okay. Now this is about what exactly reverse recovery characteristics of a diode. Reverse recovery characteristics of a diode. And we are doing some analysis. Then what this area under this triangle indicates? Reverse recovery charge. Then how to calculate reverse recovery charge. Okay. This is very important equation. This is also important equation. Then approximately you also assume these equations. Based on the data given in the problems, according to that we can apply these formulas. Understood? Okay. But here, in order to give the significance to TB and TA, here I want to define one factor. That is nothing but what exactly? Softness factor of a diode. We want to define softness factor of a diode. Then how to define the softness factor of a diode? Okay. How to define the softness factor of a diode? Now see, what is the softness factor of a diode? Yes. softness factor equal to softness factor S equal to the softness factor of diode is defined as TB by TA is called softness factor. TB by TA is called softness factor, where TB is the time taken to remove the charge carriers in junction, where TA is the time taken to remove the charge carriers in layers. Now, based on the softness factor, but in some analysis, this is also taken as a snappiness factor or softness factor, snappiness factor, or it is also called softness factor. Okay. Then softness factor equal to TB by TA. Okay. Now, based on softness factor, based on softness factor. Okay. The diodes are classified into one is, if softness factor is greater than or equal to 1, then those diodes are called, if the softness factor is greater than or equal to 1, those diodes are called soft recovery or slow recovery diodes. Soft recovery or slow recovery diodes. Soft recovery or slow recovery diodes. Soft recovery or slow recovery diodes means during turn off process. Soft recovery or slow recovery diodes means this is the characteristics. It takes more time for recovery process. Slowly it recovers. Soft recovery or slow recovery diodes. Then because of soft recovery or slow recovery, the turn off time is increases. Then frequency of operation is reduced. Hence these diodes are used for low frequency or high frequency application. Yes, these are used for low frequency applications. Used for low frequency applications. These diodes are used for low frequency application. If the softness factor is greater than or equal to 1, those diodes are called soft recovery or slow recovery diodes. Now, the second classification is, if the softness factor is less than 1 or very much less than 1. If the softness factor is less than 1 or very much less than 1, those diodes are called fast recovery or snappy recovery or transient recovery or abrupt recovery diodes. Different names are given. The second classification is, if the softness factor is less than 1, then those diodes are called fast recovery. Those diodes are called fast recovery or snappy recovery. Snappy recovery. Snappy recovery. Snappy recovery or abrupt recovery. Abrupt recovery. Abrupt recovery or transient recovery diodes. Transient recovery diodes. Transient recovery diodes. Fast recovery or snappy recovery or abrupt recovery or transient recovery diodes. Then for these diodes, during reverse recovery process, the characteristics are like this. This is sudden recovery. That is, because of this sudden recovery, turn off time is less. Once the turn off time is less, then these are used for high frequency applications. Used for low turn off time applications. 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 But point to remember, in the case of fast recovery diodes, because of large rate of change of current, this is sudden change of di by dt. During reverse recovery process, there is a large change of di by dt, sudden change of di by dt. This sudden change of di by dt causes, the sudden change of di by dt causes a large voltage across the diode, a large transient voltages across the diode. Due to that, the diodes may be damaged. Hence, practically, mainly in the case of snappy recovery diodes, in order to protect the diodes from, high rate of change of current, large di by dt, we can connect one inductor in series with a diode. We know that the inductor cannot allow the sudden change of currents. We also connect one capacitor and resistance in parallel with the diode. This is CS and this is RS. This RC combination is called snubber circuit and this is called L snubber circuit. In detail about this snubber circuit later on. But point to remember, during sudden recovery process, there is a large di by dt. Due to that large di by dt, the diode may be damaged. You want to limit that di by dt. And because of large di by dt, there is a possibility of a transient, a large voltage will appear across the diode. Then to protect that, we can use this RC combination. In detail about this circuit later on we will see. Okay, this about these diodes are called, which diodes are fast recovery diodes are snappy recovery diodes. Clear? Okay. Now this is about types of diodes based on softness factor. Based on softness factor, the diodes are mainly two types. One is soft recovery diodes and another one is fast recovery diodes. This softness factor is S. This S is nothing but a softness. But point to remember, not only due to types of diodes due to softness factor, there is a types of diodes due to application. Now I want to explain what are the different types of diodes based on application, how the diodes are classified. Now see, what are the different types of diodes based on application? What are the different types of diodes based on application? But before that, one point to remember, one observation here, you remember as a note. That means, if reverse recovery time is reduces, the frequency of operation is increases. That means, therefore, a diode with less reverse recovery time is used for high frequency application. A diode with less reverse recovery time, used for high frequency application. That's why these characteristics are very important. To select a diode for particular frequency of application. If you want to design the diode for high frequency application, means you must to design the diode with less reverse recovery time. If you want to design the diode with less reverse recovery time, means then we must to design with less number of stored charges. Understood or not? If the minority charge carriers are reduced, or if the leakage current is reduced, then the reverse recovery time is reduced, then only frequency of operation. That's why this parameter is very important for the designer or manufacturer. This is a very important parameter for manufacturer. The manufacturer you want to design for high frequency applications means you must design the diode with less reverse. Those diodes, mainly high frequency application of diodes mainly required in choppers and inverters. Where in choppers and inverters also we are using some feedback diodes, and we are also using some freewheeling diodes also we are using. Where in the case of high frequency diodes are required in choppers and inverters. But this low frequency diodes mainly required in the rectifiers and AC voltage controller circuits only. These low frequency diodes are required. Mainly that high switching frequency of operation is required mainly in the choppers and inverters. That we will see in later. Okay, that's why for designer these characteristics are very important. For manufacturer this parameter is very important to design a diode for high frequency applications. High frequency application. Okay. Now see what are the different types of diodes we are using based on application. Okay. What are the different types of diodes we are using based on application. Types of diodes, types of diodes, types of diodes based on application, based on, or simply write like this, sorry, that is types of diodes based on application. Based on application, the diodes are mainly classified into one is general purpose diodes, general purpose diodes, general purpose diodes, that is fast recovery diodes, fast recovery diodes, fast recovery diodes, Schottky diodes, Schottky diodes, Schottky diodes. Another one is silicon carbide diodes, silicon carbide diodes. That you will see in detail about what is general purpose diodes, fast recovery diodes, Schottky diodes and silicon carbide diodes. What is the application of each diodes.